In the last two sections of the book, we've defined the Riemann integral, the definite integral, as a limit of Riemann sums. We define the definite integral just over closed intervals, a, b. And then we looked at the fundamental theorem of calculus, which is our fundamental way of calculating definite integrals. However, there are integrals that come up that use Riemann integrals, but that themselves are not Riemann integrals, and they come up often enough that it's worth devoting a section of the book to them. They're called improper integrals, and they're interval integrals that involve infinity in some way. So first let me look at an example that doesn't involve infinity, but involves a half-open interval. This is an example that won't really be an improper integral, but will introduce a bunch of things that we need to look at. So let's look at f of x equals x squared. And just on the half-open interval from 0 to 1. So I've included 1, I haven't included 0. Now, of course, we know f of x equals x squared exists for all real numbers, and so it's very artificial to just restrict it to this half-open interval, but there are some points I'd like to make. Can we have a reasonable notion of the integral of this function over this half-open interval as opposed to over the closed interval? Right? With a closed interval, if I use the closed interval from 0 to 1, we would have the Riemann integral. But what about over the half-open interval? Well, that's one of the things we want to talk about. So I need to distinguish in the notation between these two. So I will subscript by the interval that I'm integrating over. So the integral over the closed interval from 0 to 1 of f of x dx. That means the same as what we've been writing is the integral from 0 to 1 of f of x dx. The question is, what should this integral over a half-open interval mean? So, what do we want this to mean? Well, hopefully you don't have to think about this too long. There's a theorem that says that the value of a definite integral doesn't depend on the value of the function you're integrating at a finite number of points. So what that means is, I didn't say that very well, you can alter the value of your function at a finite number of points in the interval, and you'll get the same definite integral, assuming you started with an integrable function. And what we've done is omit 0 here. Omit what happens at the point 0. In terms of area under a graph, you should think, oh, I left out just, in terms of area under a graph, what's the difference between the area under the graph of y equals x squared and above the half-open interval from 0 to 1 versus the area under the graph of y equals x squared and above the closed interval from 0 to 1? Well, you just intuitively, you think the area, there's no area over that one point, and they should be the same. So should we just define this to be this? Well, maybe. Let's think about other choices for a second just to make sure all the choices give us the same thing, all conceivable choices. So one other thing you might consider doing, and this is the one that we'll care about the most, is we could define this in terms of integrals over closed intervals. So what we could say is we could look at the integral of x squared dx, but instead of, well, we don't even know what this means, the integral over a half-open interval, but we could say, oh, take the integral over a closed interval from a to 1, where a is any number greater than 0 and less than or equal to 1. So this was just a Riemann integral. It's the integral of a continuous function on a closed interval. No problem. And then we could take the limit as a approaches 0 through through values that are in this interval, this half-open interval, which would mean through a is greater than 0. So from the right, so we could try taking the limit as a approaches the 0 from the right of all of these integrals over closed intervals. What will we get? Well, this now is the limit as a approaches 0 from the right of, then this is just our standard Riemann integral. And by the fundamental theorem of calculus, we know how to calculate all of these. So you take an antiderivative of x squared by the power rule, that's x cubed over 3, and you evaluate as x goes from a to 1. So then we would get the limit as a approaches 0 from the right of 1/3 minus a cubed over 3. But as a approaches 0 from the right, a cubed approaches 0, this approaches 0, and we're just left with a third. So we get a third. Well, it should be no surprise. That's exactly what you get if you take the integral, if you take the usual Riemann integral from 0 to 1 of x squared dx. You get x cubed over 3 evaluated from 0 to 1, and that's 1/3 minus 0. So that's a third. Right. So for the function x squared, even if we pretended that we only knew that it existed on the open interval from 0 to 1, so that we pretend that we know all of these where a is between 0 and 1, then we can recover the value of the Riemann integral by taking a limit as a approaches 0 from the right. And so it doesn't matter whether we look at the integral over the closed interval or define the integral over the half-open interval by taking a limit as we approach 0, we'll get the same answer either way. All right, but let's look at a function that's slightly more difficult. So let's take a look at, so here's another example. Suppose we look at, again, the integral, and I'll again write over the half-open interval from 0 to 1, because we'd like to try to decide what we want this to mean. It has no meaning as a Riemann integral. Riemann integrals are something that exist for closed intervals, but we're trying to decide what we want it to mean. So you look at this function. Okay, now we have a problem. This function does not obviously extend in a trivial way to the closed interval from 0 to 1. Right? You might go, oh, well, it'll be just like the other example. You take the Riemann integral from 0 to 1. No, this function doesn't exist at 0 because you're dividing by x. Okay, is that a problem? Well, not really. There are still two different ways we could try to approach this. One is we could define f hat of x, so something that's related to f, and I'm just writing f hat. I'm just going to let f hat be sine of x over x if x is between 0 and, so in the half-open interval. But then I'm going to define it to be 1 if x equals 0. This is called an extension of f. I haven't written what f is, so here f of x would be this, all of sine of x over x. And this kind of function is called an extension of f. It equals f where f is defined, but we went ahead and defined it at some other places. And we get to pick how we define it. So I picked it to be 1 at x equals 0. Why did I do that? Well, this f is continuous. Why is f continuous? Well, it's continuous because we actually know the limit as x approaches 0 from the right of sine of x over x. And we know it's 1. So that since the limit as x approaches 0 from the right of sine of x over x equals 1, this is a continuous function on the closed interval from 0 to 1. Right? Because this is an elementary function. It's continuous everywhere it's defined. The only place it's undefined is when x is 0, but x isn't 0 in this line. So this is continuous, and then we defined it at an extra point, 0, but as we approach 0 through the interval that we're interested in, the limit approaches the value of the function. So this function is continuous. So it's a continuous function on the closed interval. It has the Riemann integral that exists. There's a theorem, a very important theorem. All continuous functions are Riemann integrable, continuous functions on closed intervals. So that what we could say, we could set this integral from 0 to 1 of sine of x over x dx. We could set this equal to, well, the integral on the closed interval, so the Riemann integral, of this f hat function, this extension of sine x over x to the closed interval, this continuous extension. This integral exists, and we have one extra point in the domain that we're integrating over here, and we believe that shouldn't affect the integral. So we could set this equal to this. Fine. What else could we do? Well, in fact, it's nice to pick a continuous extension, but it really didn't matter. Once we know that f is bounded, so this f is bounded. How do we know it's bounded? Well, one way to know that it's bounded is to know that it has this continuous extension to 0, 1. But then this is a continuous function on a closed interval, and the extreme value theorem tells you it obtains a maximum and a minimum value, which means once you throw away this point, this function had to be bounded between the maximum and minimum values of this. So this function is bounded, and if you define f hat of x to be anything, you could just define it to be any real number here. This is going to be a bounded function, and it's going to be piecewise continuous, no longer necessarily continuous, but it's bounded and piecewise continuous, and that's enough for the Riemann integral to exist. And so regardless of how we define this extension, this integral exists, and we could use it to define that. You might say, oh, but if I take different extensions, maybe I'd get a different answer. No. There's a theorem that says if you've got two functions and they only are different at a finite number of points, then one's Riemann integrable if and only if the other one is, and their Riemann integrals agree. So every single extension of f to an f hat has to give you the same integral over the closed interval from 0 to 1. So yeah, if we wanted, we could define this to be this, where f hat is just any extension whatsoever of f. What's wrong with that? Actually, nothing, except it won't generalize to the next case that we're going to look at very well. And also, somehow it's a little unsatisfactory. It's not, just doesn't feel right to have to define this function at places where originally it doesn't exist in order to talk about the value of the integral. So there's another approach that we take where, like what we did in the last example, where we take limits. Instead, we can also define the integral over this half open interval of sine of x over x dx we could define this to equal the limit as a approaches 0 from the right of just the Riemann integrals. So the integral from a to 1 of sine of x over x dx. For a between 0 and 1, this integral certainly exists because this is a continuous function as long as a isn't 0. And then you can take the limit as a approaches 0 from the right. What do you get? Well, we're not going to calculate an antiderivative of sine of x over x. But we don't need to. In fact, it's true that for Riemann integrable functions, which we now know sine of x over x extended in any way whatsoever, that's Riemann integrable because it has a continuous extension, and so the integral we get, that's Riemann integrable, but then so is any function we get by changing f hat at a finite number of points. So we know that we have integrals like this, but then it's a theorem that the Riemann integral is continuous as a function of its endpoints. So as you approach, for integrable functions, so as a approaches 0 from the right here, what this would what this would equal is exactly this thing above for any value of f hat. So the point is, in this example, it doesn't matter. No matter what approach you take, no matter which approach you take, to trying to define the integral of sine of x over x dx on this half-open interval, you get the same thing. You can either take an extension of f, any one whatsoever, to the closed interval from 0 to 1, or you can take limits as a approaches 0 from the right of Riemann integrals of sine of x over x. All right. What's an example where one of these approaches works and the other one doesn't? So where taking limits works, but taking extensions would not. Well, let's look at the integral. Again, we'll just stick with the half-open interval from 0 to 1, but let's look at 1 over x to the 1/3 power dx. We would like to try to make sense of this as some kind of integral, or in terms of integrals. And in terms of areas, again, you should think you take the graph of y equals 1 over the cube root of x, so roughly it looks like the graph of 1 over x. And we're trying to look at the area above 0, 1 where you don't include exactly 0. Well, that'll be hard to draw. You would hope it's the same as the area if you did include the endpoint 0, because all you're leaving out is a line, and you'd like to think, oh, that has 0 area, even though it goes up infinitely far. All right, so you're calculating this area, but the question is, what does this mean? And what you can't do is extend this to a Riemann integrable function on the closed interval from 0 to 1. F of x equals 1 over x to the 1/3 power is not, let me say is unbounded. It is unbounded on 0, 1. That is, the value of f is getting arbitrarily large as x approaches 0 from the right. But it's a theorem. Unbounded functions do not have Riemann integrals. So if we extend this to a function f hat on the closed interval from 0 to 1, well, because this is already unbounded, f hat would be unbounded. So if we try to extend this to the closed interval from 0 to 1, we'll have an unbounded function, and it is not Riemann integrable. So if we're going to say this integral exists, it really is a new kind of integral for us. It is not a Riemann integral. These we could have interpreted, like when we were over here, we could interpret this as a Riemann integral of an extension. This is not like that. But what about our limiting kind of definition? Could we define this in terms of limits if we wanted to? The answer is yes. We could once again take the limit as a approaches 0 from the right of, well, of the integrals over closed intervals. So I'll now write 1 over x to the 1/3 is x to the minus 1/3. We could do this where this is just your standard Riemann integral because we're using a's that are less than or equal to 1 and greater than 0. This is continuous. This is a closed interval. This is Riemann integrable. So this is just the limit as a approaches 0 from the right of, I'll just write it in the standard notation, the integral from a to 1 of x to the minus 1/3 dx. But now you apply the fundamental theorem. This is the limit as a approaches 0 from the right of, you use the power rule. You add 1 to the exponent. So we need an antiderivative of this. You add 1 to the exponent and divide by the new exponent, and you get x to the 2/3 divided by 2/3, and you evaluate this from a to 1. So what do you get? You get the limit as a approaches 0 from the right of, this is, you evaluate at 1. So we get 1 to the 2/3 over 2/3. So we get 3/2 minus 3/2 a to the 2/3. But as a approaches 0, a to the 2/3 approaches 0, and this approaches 3/2. So this limit of Riemann integrals exists, and we could use that to define the integral over the half-open interval. So, in fact, we do. We define, in this case, we would define the integral from 0 to 1 of 1 over x to the 1/3 dx. We would define that notation to mean what I've called the integral over the half-open interval. So, and we define that to mean the limit. Which we just saw was 3/2. So that's what we do. We use this notation that we would use over the closed interval because if this function does extend to the closed interval and is bounded so that it's Riemann integrable on the closed interval, so that's when we would use, that's the other time when we would use the notation integrate from 0 to 1 if this function were Riemann integrable over the closed interval from 0 to 1. If we start with a function that was Riemann integrable on a closed interval, then as we saw before, the Riemann integral and the limit of these Riemann integrals will give you the same thing. So it doesn't matter that we're thinking of this as over the half-open interval. But this notation is more general now. It doesn't just apply to Riemann integrals. We have to take limits at these problem points since this function approaches infinity as x approaches 0, we have to take a limit to calculate what we want to call the integral of this. Before I make the definition in more generality, I do want to look at another way that infinity, so kind of unboundedness, comes into integrals that we care about. So let's look at another example Let's look at the integral from 0 to infinity of e to the minus x dx. This function is not unbounded. It's strictly decreasing its derivative. In fact, let's do that. E to the minus x, the derivative is, you get the e to the minus x back, but by the chain rule, you have to multiply times the derivative of minus x times a minus 1. E to anything is positive, but it's times negative 1. This is negative. This is a strictly decreasing function. It's always greater than 0. In fact, you can graph it. It's, looks like the graph of e to the x, except reflected about the y-axis, because we replaced the x with negative x. So here's 1. And what this integral, assuming we had some idea of what it means to integrate out to infinity, if this integral exists, what it should be calculating for us is the area under the graph of y equals e to the minus x and above the interval from 0 to infinity. So it's calculating the area of this region that goes out infinitely far. How do we want to calculate this? Well, you probably can guess at this point what we're going to do. We're going to set this equal to the limit as b approaches infinity of the integral from 0 to b of e to the minus x dx. Again, this is a continuous function. It's integrable over any closed interval. So 0 to b, it's a closed interval. And you just take the ordinary Riemann integral of this, but then you take the limit as b approaches 0. We use the fundamental theorem. We have to produce an antiderivative of e to the minus x. I will leave it to you to verify that an antiderivative, well, I can say it. Minus e to the minus x is an antiderivative of e to the minus x. If you differentiate this, as we saw, you get minus. If you differentiate that, you get minus e to the minus x. So if you differentiate this, you get e to the minus x. So the fundamental theorem tells us to calculate this integral. You take this antiderivative and you evaluate from 0 to b. So we get So what we get is the limit as b approaches infinity of negative e to the minus b minus what you get at 0 is this. As b approaches infinity, this exponent approaches negative infinity, e to the negative infinity. You should think 1 over e to the infinity, 1 over something super big is really close to 0, and in the limit this goes to 0. And so we're left with negative, negative 1. So 1. So it may not, I hope it's not obvious, but yeah, the area under this graph is exactly 1 if you go out infinitely far. All right, so what is it that we're saying? Well, I could write, I suppose I should write a careful definition. So the definition we want to assume that our function is given on a half-open interval and is integrable on every closed interval contained in that half-open interval. So suppose I'm going to state it for half-open intervals on one side and then say how to change it for half-open intervals on the other side. So suppose f is defined on a half-open interval of the form AB, where a is allowed to be minus infinity. And we're also supposing for all c in there, for all c such that A is less than C is less than or equal to B. For all the Riemann integral from C to B, I'll write the Riemann integral. The Riemann integral So this is the case what we've been looking at. We had a function, it was defined on some half-open interval. We knew that our function was continuous, so we knew in fact that it was Riemann integrable on any closed interval contained inside it. That's the usual case where you'll assume f is continuous on this, so that this condition that and so for any closed interval contained in here, this integral exists. That'll be automatic if you know f is continuous on your half-open interval. In this case, we do what we've done so far. You define the integral from a to b of f of x dx to equal. This really requires a definition for our functions if they become unbounded, or if a is negative infinity, to equal the limit as c approaches a from the right of the Riemann integral from c to b of f of x dx. So don't let all the variables confuse you. This is exactly what we were doing. You want to know what an integral means, but your function has a problem at a. You take the limit as you approach a. As you approach a, how? Well, you only care about approaching a through x values in this interval from a to b, and assuming a is, I should have assumed that. I meant for a, b, a is less than b, otherwise this wouldn't be an interval. But, okay. So this is what we were doing. We set it equal to this. If f doesn't have a problem at a, so if f was already Riemann integrable, as I said, this gives you the same as the Riemann integral over the closed interval from a to b. But in other cases, like when f is unbounded, this could actually give you something new. We define this to equal that, provided the limit exists. And if the limit exists, in this case, so in the case that the limit exists, we say that f is integrable without modifying it by the word Riemann. We just say f is integrable on the half-open interval. Or we say the integral converges. Otherwise, we say that f is not integrable on the half-open interval from a to b, or we say that the integral from a to b of f of x dx diverges. So, okay, so this is an extension of our notion of integration to functions that may not be Riemann integrable, but we want this limit of an integral to have meaning. What do you do on half-open intervals that go the other way? You make all the appropriate changes. I hope those are fairly obvious. If f is defined on this half-open interval, where b may be positive infinity now, as in our example, then for all c, now we want this, the Riemann integral from a to c. Then we set this equal to the limit as c approaches b from the left, the integral from a to c, provided the limit exists. Right. Okay. So this is what you do, but this is provided that our domain over which we're trying to integrate is just a half-open interval. And there are worse kinds of problems. You could put together activity on half-open intervals and come up with kind of a messier problem. And I want to look at that. But first, I haven't said what an improper integral is. So let me say that. Some sources will tell you that an improper integral is just a limit of these Riemann integrals. Others will say what I'm going to say, which is that this integral is improper. So our definition is that this integral is improper if a or b is plus or minus infinity. So we say this is an improper integral in the cases where something bad could happen, where we have to take limits, where we couldn't use extensions and normal Riemann integrals. So it's an improper integral if infinity is involved somehow. So a or b or plus or minus infinity, improper integral. A or b is plus or minus infinity, so that your limits of integration involve infinity, or f of x is unbounded. On the open interval from a to b, which would include being unbounded on the half-open intervals, because if you're unbounded there, you're unbounded on the half-open interval, and if you're unbounded on the half-open interval and you delete what happens at one point, you'd still have to be unbounded, so you'd have to be unbounded here. Anyway, that's an improper integral, one that involves infinity somewhere where you're trying to integrate. And those are the ones where we have to take limits as you approach the problem points. I say problem points because there could be more than one. So let me just write a couple. So here's another example. What about the integral from -1 to 8 of 1 over x to the 2/3 dx? You may look at this and think, well, this isn't an improper integral. It doesn't have a problem. This is a continuous function. It doesn't have a problem when x is -1. It doesn't have a problem when x is 8. What's the problem? The problem is, neither one of these are infinite, -1 and 8. But the problem comes in that 0 is a problem for this function. This function becomes unbounded on the interval from -1 to 8 because that includes 0, where this does have a problem. So what do? We talked about what to do if your problem occurred at the endpoint of a half-open interval, but it's in the middle of it's in the midst of this interval. What do? The answer is you split up the integral at 0. So we want to split up the region that we're integrating over, the interval that we're integrating over, into pieces where each piece has a problem at most at one of the endpoints of the interval, so that you break this up at 0. Right? You say, oh, the integral from -1 to 8 should mean, and we go ahead and extend our definition of integration to extend this property that we had for Riemann integrals. You want the integral from -1 to 8 to be the same as you integrate from -1 to 0. And you add to that what you get as you go from 0 to 8. Now, this function on this interval has a problem only at this endpoint, 0. So it's a problem on a half-open interval. Same thing over here, that we know how to deal with this integral. We take limits. So you take these two. By the way, these limits are supposed to be separate. If either one of these fails to exist, you say that this improper integral does not exist. If either one of these fails, for the integral to exist, when you split it up into pieces like this, you need for each piece to exist. But they will. I'll leave it as an exercise, but you take the limit here as b approaches 0 from the left of the integral from -1 to b of 1 over x to the 2/3 dx. And you add to that the limit as a approaches 0 from the right of the integral from a to 8 of 1 over x to the 2/3 dx. I'll say it again. So you use the fundamental theorem to calculate each one of these, and then you take the limit. You'll see that both of these exist, and so we say that this exists or converges, and it equals the sum of these two. If either one of these had failed to exist, we would say that this diverges and the improper integral does not exist. How bad can this get? Well, it can get, you can put as many problem points in as you want in theory, so you could, this would be awful, but actually it wouldn't be that awful, but it would look awful to start with. Suppose I want the integral from 1 to infinity of 1 over x minus 2 times x minus 4 dx. Okay, you see it's an improper integral because you go out to infinity. All right, is there any other reason that it's improper? Yes. This function becomes unbounded. As x approaches 2 from the left or the right, this becomes arbitrarily big. So there's a problem when x is 2. There's a problem when x is 4. So we have 3 problems in this integral. There's a problem at x equals 2. 2 is in this interval. If this had been a plus 2, so that this had a problem when x is negative 2, we wouldn't care because we're integrating from 1 to infinity. And minus 2 wouldn't be in there, but this is a minus 2, so it has a problem when x is 2, problem when x is 4, and then you have to go out to infinity. So you have to split this integral up into how many pieces? Well, more than you might think. So you would take this to mean the integral from 1 to, okay, you can, there's a problem at 2, fine. So you take this. And then you'd like to go, okay, and then you pick up your integral at 2, and you go to, and you might think you go to 4. And write the integrand over again. But you don't want to do that. You want one problem place per integral. And our integrand has a problem at 2 and at 4. We don't want 2 problems. We don't want to take 2 kind of simultaneous limits. So what do? You split up the integral any place between 2 and 4. It doesn't matter where. You'll get the same answer no matter what you do. But you need to split up the integral somewhere. 3 would be the obvious place between 2 and 4. But maybe just to emphasize that it doesn't matter, I'll pick 2.5. It doesn't matter. You just want to pick some place between 2 and 4 to split up your integral. So go from 2 to 2.5 and integrate the same thing. And then you pick it up at 2.5, and then you go to your next problem point, 4, and you integrate the same thing. And then you pick it up at 4, but you only want one problem per integral, so you don't want to go from 4 out to infinity, so you go anywhere you want, someplace between 4 and infinity, 7. I just made that up. It doesn't matter what you pick, but you want to split it up again. And finally, you would add to this the integral from 7 to infinity of 1 over x minus 2 times x minus 4 dx. So this would be your approach to dealing with this integral. As you can see, it can get messy. What you want to do is split your interval that you're trying to integrate over into pieces, into subintervals, so that your integral has a problem only at one endpoint of each subinterval. So you go from 1 to 2, and then you go from 2, but you don't want to go to 4, so you all the way to 4 because the integrand has a problem at 2 and 4. So you go to anywhere between 2 and 4. I went to 2.5. Pick it up at 2.5 and go to 4. You can't go from 4 to infinity because you don't want two problems. So you go from 4 to 7. Then you go from 7 to infinity. For this integral to converge, you need to know that all 5 of these converge. If any one of them fails to converge, we say that this integral diverges. In fact, this will diverge, but we would have to do a partial fractions problem, which isn't the point of this section. But the point is, improper integrals. You look for, well, infinite limits of integration are easy to spot, but you also need to look at places where your function gets infinitely big or infinitely negatively big, so it goes to positive or negative infinity, because that means your function is becoming unbounded as you approach those points. Then you have to split up the domain into subintervals where you only have a problem at one endpoint of the subinterval, and then you have to calculate all of these improper integrals, so each one of these will require a separate limit. But if you find one of them that doesn't exist, you can stop. That means the original integral does not exist, so the integral diverges. But if all of them exist, then we say this one exists and it equals this sum. Okay, I believe we'll leave it there. We could do lots more examples, and we could actually calculate this one, but that would be tedious. I wouldn't want to do it, and you wouldn't want to see it. So next time, we'll start with numerical integration, which is a way of dealing with integrals, or a way of approximating integrals that we can't do by the fundamental theorem, or can't do easily using the fundamental theorem.